So this is in continuation to the previous lesson video. In the previous lesson video, we looked at the region bounded by the graph of x squared plus y squared is equal to 4, which is a circle centered at the origin with a radius of 2 units. And we wanted to build a solid on top of this region. This region is in the xy plane. We're not going to revolve this region, but instead we're going to treat this circle as the floor of our solid, and we'll build up from it towards the sky. In the previous lesson, we went over how this works. We went over the development of the integration formula that would give us the exact volume for this solid, and this is what we came up with. We need to find a function of x that would give us the area of each cross section. We talked about why we're integrating with respect to x when our cross sections are perpendicular to the x-axis. So you can refer to the previous video to understand why. And we also talked about how we come up with the limits of integration. In the previous video, we looked at the same example, but the cross sections perpendicular to the x-axis were squares, and now we want to look at what happens when the cross sections perpendicular to the x-axis are semicircles. We are in fact using the same general integration formula where the integrand has to be a function of x that would give us the area of each cross section. So what happens when our cross sections perpendicular to the x-axis are semicircles instead of squares? So let's take a look at that. So we began with finding the length of an arbitrary vertical line segment between the top and the bottom halves of our circle, and we were able to do that by solving our equation for the circle for y. The equation for the top half of the circle would be the positive square root of 4 minus x squared, and the bottom half of the circle, negative square root of 4 minus x squared. The length of a line segment between the top and the bottom halves of the circle, you can call it r of x if you want, you can call it something else. For example, you can call it L of x just for length. That's going to be top minus bottom, and we have this. And when you simplify that, you will get L of x is equal to minus negative is plus, so you have two radical expressions that are like radical expressions, so you have 2 times the square root of 4 minus x squared. So now what we have is a function of x that would give us the length of an arbitrary line segment between the top and the bottom halves of our circle. Our cross sections taken perpendicular to the x-axis are semicircles, so let me draw 3 of them here. So they'll look something like this, and I'll try to draw them in different colors so we can still distinguish between them. So they'll look something like this. And the integration formula that we have is volume is equal to the definite integral from a to b of a of x times dx. So the limits of integration would be from x is equal to negative 2 all the way to x is equal to positive 2. Our semicircles start at negative 2 and they end at positive 2. So we're going to have volume is equal to the definite integral from negative 2 to positive 2. We're integrating with respect to x because how do you find the volume of each semicircular approximating? How do you find the volume of each semicircular solid, and a bunch of them together is approximating our solid? You need to find the area of the semicircular base and multiply by the height, which is going to be, in this case, given by delta x. So that's why we integrate with respect to x. So how do you find the area of a semicircle? Well, you find the area of a circle and divide by 2. And how do you find the area of a circle? It's pi r squared, and then divide by 2 to find the area of a semicircle. So that's what we need to do. And when we've done that, we'll have our integrand, a of x, and we'll be done with our problem. So what's going to give us the radius of each semicircle? What function of x is going to give us the radius of each semicircle? L of x that we found earlier will give us the diameter of each semicircle, and to get the radius, you can take the diameter and divide by 2. So the radius of each semicircle would be the diameter that we found earlier, which is right here, 2 times the square root of 4 minus x squared divided by 2. So it's going to be the square root of 4 minus x squared. And what do we need to do with this? To find the area of each semicircular base, you need to do pi r of x squared, which will give you the area of a circle, but then you have to divide by 2 because you have a semicircle. So with this, we're now ready to write our definite integral that will give us the volume of our solid. The base is bounded by the graph of x squared plus y squared is equal to 4, which is a circle centered at the origin with a radius of 2, and cross sections perpendicular to the x-axis are semicircles. And let's go ahead and write our integral for it. So following our general formula, we have volume is equal to the definite integral. Our x values start at -2 and they go all the way to +2. So we have our limits of integration. We know we should integrate with respect to x because our cross sections are perpendicular to the x-axis, and the integrand is going to be a function of x that will give us the area of each cross-sectional surface, which is a semicircle. So how do you get that? You need to find the area of a circle and divide by 2. And how do you find the area of a circle? Pi r squared. What is the diameter? The diameter is the length of this vertical line segment, and then you take that and divide by 2 to get the radius. So now that we have a function for the radius, which is right here, we're going to square it, multiply by pi, and divide by 2, and that's going to be our integrand. So we're going to have the square root of 4 minus x squared. That's the function for the radius. We're going to square that, so the square root will go away, multiply by pi, and finally divide by 2. So we can just simplify it a little bit. Pi is a constant with respect to x, so is 1/2. So you can factor out the constant factor of pi over 2. So we can factor it out of the integrand or the integral, and then the limits of integration are from -2 to +2. So what are we left with in the integrand? The square root of 4 minus x squared squared. So when you square, it will undo the square root, and you're going to have 4 minus x squared for the integrand, and you're integrating with respect to x. So this is going to be how you find the volume for our solid with cross sections perpendicular to the x-axis being semicircles.